everybody. Welcome back to Earth Space. We'll be doing something completely different today. We are finally done with the astronomy unit of the course, and so we're getting into weather or meteorology. So this is definitely a chapter. Today, that's it. Long. If you need any highlighted or old names that I have in these notes in a Google Doc and submit them in Canvas just like we've always done before. So to start out this discussion, we need to talk a little bit about the difference between weather and climate. Weather is what's happening right now outside, or what happened yesterday at 3 o'clock outside. It is sort of the current conditions. It's the conditions over a shorter period of time, and it's constantly changing. If we're going to start talking about climate, though, we'd want to discuss long-term averages. What is the average temperature on April 21st over 120 years of records, for example? Or what's the average amount of snowfall that we get in a typical January? What do we typically study or measure when we study weather and meteorology? Things like temperature, humidity, how much water is in the air, percentage of the sky that's cloudy, precipitation, how much water, either rainfall or snowfall, falls from the sky. Air pressure, we'll talk about in a future chapter, is important to understanding why what happens, why the weather we get happens, and also wind speed and direction. Well, if we're going to study weather, we need to understand what the atmosphere is made of. Major components of air are nitrogen, oxygen, and carbon dioxide. Doesn't seem like a very big amount, 0.0397%, but actually it has a huge effect on our atmosphere and its properties, and we'll talk about that later. There's just a pie chart showing those relative percentages. Also, the water vapor in the air is important. It only makes up about 4% of the air, but it's important to realize that 4% of the air around you is actually water. You probably realize that this forms clouds and precipitation, but it also has another important role in that it absorbs energy from the earth and stops heat from escaping back into space. Aerosols are tiny dust, smoke, or salt particles. They're important because clouds form due to them. We'll talk about that later. There's also an important component of our air called ozone. Instead of O2, the oxygen that we breathe, ozone is O3. It actually absorbs some harmful ultraviolet radiation that comes from the sun. This is the type of radiation that gives you sunburn and also gives you skin cancer. Humans have released pollutants called chlorofluorocarbons that have depleted the ozone layer. Fortunately, we have banned those, and the ozone layer is gradually recovering slowly over the years. This is not the same as global warming, however. There's a map of the ozone hole over the Antarctic region of the Earth. Next, we're going to talk about what the atmosphere is made of in terms of its structure. What happens throughout the atmosphere as we go up towards space? The first thing is the pressure changes. It starts out at about 15 pounds per square inch of pressure down here, and it drops as we go up. There's a graph showing that if you were to climb to the top of Mount Everest, the pressure would be less than half of what it is down here. That's why climbers that climb to the top of Mount Everest typically have to bring oxygen tanks along with them in order to breathe properly. The bottom layer that we are in is called the troposphere. Temperature drops as you go up. The reason for that is because the sun heats up the surface of the Earth, and the warm surface of the Earth heats up the air down here in the troposphere. So the farther away you get from that warm surface, the lower the temperature is. When we get to the stratosphere, that's typically where planes fly, the temperature starts to go up. The reason for that is because that's where the ozone layer is. Remember that ozone layer absorbs ultraviolet light, making it get hotter up there instead of colder. Above that, we have the mesosphere, where the temperature begins to decrease again. And finally, the thermosphere, where the temperature increases again. This happens due to the fact that there are high energy particles coming from space, coming from the sun actually, that impact the Earth's atmosphere and make it very hot here. This is where the northern lights or the aurora borealis are located. There's a graph showing what we discussed. We've sort of already talked about the Earth's seasons and how the sun, Earth, and moon move, so we're sort of skipping this section of the notes. We've discussed this at length in astronomy already. discussing the winter and summer solstice and the equinoxes in fall and spring. Out of daylight you get. How this affects the weather, obviously, is that as you get more daylight, the temperature is warmer. If you get less daylight, or that sun is at a lower angle in the sky, the temperature gets colder. This is the reason we have the seasons that we do, that tilt of Earth's axis as it orbits the sun. Where does the heat come from in our atmosphere? Well, uh, heat moves. That's the first thing we're going to talk about. That's called heat transfer. It moves through conduction, convection, and radiation. These are three heat transfer processes you've probably learned about in a middle school or elementary school science class. Conduction means direct contact. Convection means moving warm material, and radiation is energy with light. Well, what happens to that energy coming in from the sun? That's what this little section is about. First thing that can happen is it can reflect, it can bounce back into space. The second thing is it can scatter around, it can make the sky look blue. Uh, and the third thing is that it can be absorbed, it can heat up or warm up whatever it's striking. So something interesting happens if we take a look at radiation that comes in from space and then tries to get back into space. What it does is it re-radiates that radiation in the form of infrared energy or heat energy. It tries to leave as heat. So what can happen is that that heat can be absorbed or trapped by some different substances. Carbon dioxide, water vapor, and actually methane are the three greenhouse gases. The whole idea that water vapor and carbon dioxide trap infrared or heat energy from escaping into space is called the greenhouse effect. This is different from global warming. I want to make that point here. The greenhouse effect is good. We need the greenhouse effect. If water and carbon dioxide were not trapping energy, keeping it here on the surface of the Earth, our Earth's temperature would drop to 200 or 300 below zero at night. So life is possible on Earth because of the greenhouse effect. Places like the moon, there is no greenhouse effect. And so it does drop to 300 below zero at night on the moon. That's showed on the left. On the right is shown Venus, where you have a runaway greenhouse effect. The temperature is 8 to 900 degrees or more on the surface of Venus because nearly all of the energy from the sun is trapped by Venus's thick carbon dioxide atmosphere. We sort of have a balance between the two on Earth in the middle. This next section is about what makes the temperature what it is at certain places on Earth. The first thing that controls temperature is altitude. We talked about this earlier, but the higher altitude you have, the lower the temperature. The second thing is where you're at in relationship to the coasts. So, for example, you see that city in California, the temperature doesn't change very much because the ocean is pretty much always the same temperature year round. Winds are coming off the ocean there in Eureka, California. And so in the summer, it doesn't get very hot. And in the winter, it doesn't get very cold. The temperature, average temperature is pretty much always between 50 and 60 there in Eureka, California. However, in New York City, they typically always get air off of the land or a continent. Land cools much more quickly at night and warms up much more quickly in the day. So they have more extreme temperatures. Their highs are higher and their lows are lower. Cloud cover matters too. Clouds block sun. You probably realize that clouds can block sun and reflect light back into space. So a cloudy day will be cooler during the day than a clear day. What you might not realize is that cloudy nights are warmer than clear nights. Clouds act as a blanket. Remember, water vapor is a greenhouse effect, or is a greenhouse gas, and clouds trap heat in the atmosphere at night. So a cloudy night is warmer than a clear night. These are kind of some general concepts that make sense. Temperature decreases as you go toward the poles. That makes sense. Isotherms exhibit a latitudinal shift with the seasons. That just means that it's warmer in the summer and cooler in the winter. And three, the warmest and coldest temperatures occur over land because of what we just talked about. Land cools off much easier than water, and it also warms up much quicker. than water. Water has a very high specific heat. It takes lots and lots of energy to heat up a kilogram of water by 1 degree versus a kilogram of rock or land. Again, annual temperature range is pretty small near the equator. It's warm all year. The annual temperature range increases as you get closer to the poles. That is to say, the difference between the hottest and coldest temperature increases as you go toward the poles, and it's greatest over the land. Different maps showing that average temperature in January and July. And that's it. Hopefully, this gives you a brief introduction to weather and meteorology. Again, copy down the items that I circled into a Google Doc, submit it in Canvas as we always do, and have a good day.